try. Ooh, it was on Friday. Let me put this up on the board. Don't look at me with three little cherub faces and say, no, we didn't. Because we did. Just saying. Okay, I believe I looked back at Friday's subnote. Now, I know Friday was a day where you guys got to go see the, no. Not, that was you guys, that was block 4. Yeah, okay, I know. Okay, so it should be page 265 to 267. It was numbers 2 to 8. And these were just kind of big idea questions. They weren't using the fundamental theorem of calculus just yet, the thing that I taught you yesterday. That's in 18, although it doesn't quite look like it. They were, once again, big idea kind of type questions. So, supposedly, you were given this on Friday by the mean lady. I don't know who that is, because...
Wait, was the lady on Friday really nice?
No, everybody in my distance was like, this was the wicked witch of non-paraphrasing. I should just say the mean lady, as the case right there.
The difference is we went Friday
Now,
and Tuesday.
in section 2, on page 265, you guys were going to find that you didn't need that fundamental theorem of calculus because I fully did not want you to learn it on your own or do it without my help explanation. Do you know what I'm saying? So this has to do with graphs of functions and graphs of derivatives, okay? Because you've now learned graphs of, well, how do I want to say this to you? Let me say it this way. Remember from yesterday, when we talk about x to the 5th dx, you now know there's a rule that says what we do is we add 1 to the exponent and then put 1 over that number in front. And you learned a lot yesterday in a very brief amount of time. You learned that sometimes we refer to this symbol as the antiderivative because you're going from the derivative to the original function. You also learned that we call it the integral when we're talking about finding the area between it and the x-axis. And you learned how to do this kind of a problem. Let's say, for example, if you had x to the 5th and I asked you guys to try to find the area between 0 and 2, but I didn't give you any more homework over that yesterday. I just simply said, take a look at Friday's stuff. So up in orange, up here is Friday's stuff, and I can see if I can try to help you with that, or we could, I guess I already kind of said I should do it that way. I should probably do it in that order. I won't change my mind. I have so many orange markers up here, it's like an attack of orange markers.
Yeah, there's a ton of them.
I know. It's like, they're everywhere.
There's like 8 of them over here too.
Yeah. I guess our subs like orange markers. I'm not really sure. So, you guys were looking at 2 through 8. And 2 through 8 are pictures. Well, they're not pictures. They were tables. Some were pictures, some were tables. I'll just kind of step back and open the floor up to you all, because it's not all about me understanding what's going on. It's sort of, you guys. So let's take a look at like problem number 2. Number 2 gives you a sketch, and it said, and I'm bad when it comes to this, reading the instructions. I have to be really careful and make myself go back and go, read the little paragraph up at the top. So it says, they're going to give me, oh, no, I take it back. It's in exercises 1 to 4. It says, sketch 2 functions f that have a derivative where f prime is the graph that's shown. So in one case, let f of 0 equal 0, in the other case, let f of 0 equal 1. So, number 2, and again, I don't know necessarily that you guys need me to start here, but it's getting at what's going on. It just didn't do it with calculus. So the number 2 that you guys see, let me see if I can draw this. It looks kind of like your paper. It looks like it goes through that. It looks like it's a straight line. It goes through 1, and then this little blue curve is called f of x. Oopsie. Okay. So, if you take a look at this, a few ways to do this. One, we could do this analytically, where we guess at the equation for the original function, and then we come up with what our graph should be. Or, what we could do, okay, so guys, here's the way this is working. What they're doing in problems 2 through whatever the end of this section is they're giving me the sketch of the derivative. And they're asking us to come up with two possible sketches for the original function. Okay, just to kind of explain to you what's going on. Now, what I want you to think about, I'm going to leave myself some room, and I'm going to come through here and give myself two graphs, so two possibilities. And I'm going to do this with you graphically, okay? Now, whenever I'm trying to sketch a graph of the original function, they said do this with two possibilities, so option 1 would be here, option 2 would be here. It helps me tremendously to have that first derivative number line right underneath it. Do you know what I'm talking about? You've seen that before, okay? Now, if I look at my graph up here, this is the derivative. So even though they call this little f, it's the derivative of f of x. So I want you to look at that and go, that's the derivative. Now, what that information is telling you is this. It's telling you at x equals 1, you have a value on your derivative that is 0, because isn't that a y value of 0? So here's what that means in calculus. That means that at 1, the derivative is 0. Do you remember the definition for critical values? Critical values are places on your graph, either where the derivative is undefined, or 0. So that means that at 1, my graph would have a critical value. So for both of these, my graph would have a critical value there. Now, let's take a look at the left side of this. Do you notice that the left side of this has all positive values on the derivative? So that would mean for both of these that the left side of 1 would have a positive derivative. You guys know that that means the graph would be rising in that area. Are you with me there? Okay. And then this part of the graph, because it's down here, has derivatives that are negative. So this is negative, which means that has to fall. This is negative, which means that has to fall. These both are going to look very similar. They just gave you, what they're trying to get at is, we're describing tons of functions. If we don't know where to place these, all we know is that our graph goes up to where x equals 1 and comes down. Okay? But that could mean that your graph, okay, wait, before I get to that, let me also ask you this, before I start sketching. When the derivative is 0, does that mean that you have a flat turnaround spot, or does that mean that you have like a sharp kind of turnaround spot? If the derivative is 0, it means it's flat. So the other thing that I want to put on both of these is that this at x equals 1, my graph is supposed to have a flat spot. Now there's one more piece of information in number 2. Number 2 says, or in the directions, they say in one case let f of 0 be 0. So they want 0, 0 to be on the graph of the function. And in the other case, they say let f of 0 be 1, which just means they want 0, 1 to be a point on the graph. That's all they're saying. Because the idea is, guys, we could draw this anywhere we want. If they said 1 is supposed to be the maximum, you could have the maximum point being up here and going down on both sides. It might be here. It might be down here. Do you guys see how there's like infinitely many possibilities just for that shape? The only thing that has to happen about it is it's a concave down parabola and its flat spot is above or below x equals 1. So they want us to draw the graph so that it goes through the point 0, 0. Well, let's go over here and go x equals 1 would be the point where the graph is flat. So I just need to draw it so that my graph is flat at that spot, has a maximum, and it goes through 0, 0. The other one, they want me to make it go through here. Well, at x equals 1, that would mean that it would have to be higher than that. So they just want you to see that in this case, there's many, many, many functions that satisfy this basic shape. Do you guys see what I'm saying? I mean, we could be here all day. As long as the flat spot is at 1, it could be any of these. So it was just trying to say, hey, draw 2 of them. Draw one of them where it goes to the origin, and draw another one. So this was the specifics and the directions. Draw one where the graph goes to the origin, and one where the graph goes to the point 0, 1. So that's all that was doing. It's probably best if we just do this graphically, because I think graphically, sometimes some of you are more geometric kind of people. I'm not as much, but I need to make sure that I'm covering all my bases, and you need to be able to see it both ways. So I just did number 2 with you. If that helps, great. If you'd like to look at more, we can do that too. I'm totally happy to do that. But when I do this problem, it helps me tremendously to go, here are my places where I'm going to draw my function. Let me take a look at what my number line is, because when I see the number line and I fill that out, then I'm like, okay, I get my picture. Remember, this is like a stick figure drawing of your graph, right? Remember that kind of deal a little bit? Yes, sort of good. You got at least one yes. So that's that one. Number 3 is going to be kind of the opposite of it, because the graph on number 3 for the derivative that they gave you in the book is actually a line that's heading upward. But I'll just ask you guys on any of the ones from 2 through 4, because those all have the same directions, if you have questions on 2 through 4, because again, I had you doing 2 through 8, but I'm open to doing any of these out of order. I just thought I'd start with 2 just to give you an idea of how to approach that. So if you need 3 or 4, that's fine, or 5 through 8, whatever, not all of them, but anyways. Figure I'll spend about less than half the class on this, and then I'll start you on your homework for today. Or whatever the case is, yes. Can we look at 4? Absolutely. Okay, good question. All right, so 4, let me do this over here. So the sketch in your textbooks, if you don't have a textbook out, it's totally fine. Looks like this. And tell me if I'm wrong, Donovan. It looks like an absolute value graph that touches at 1. Is that right? Okay. Now this is the derivative. Everyone agree with this? Okay. Now I'm going to be sketching 2 functions. They want me to do this twice. So here are my 2 options. Option number 1, they want to make sure it goes to the point 0, 0. Option number 2, they want to make sure it goes to the point 0, 1. We'll get to that. But what I want to do is draw the number line for f prime, because this will help me figure out what my shapes are going to be. They're both going to have the same shape. One's going to be a little higher than the other. That's the only thing that's there. But it might be like, not so sure about this. Okay, now, let's take a look at this. This means that at 1, your slope is 0. So that means that's a critical point, just like in the last one. So there's 1, and there's 1. Do you all agree with that? Okay, beautiful. Now, let's look at this. All of these points up here, which I will trace, are positive or negative. These are all positive y values, right? I'm saying, I should have said, what y values do you have? They're all positive, right? Now, what I want you to notice is this. These were the biggest y values. So that would mean like at -1, you've got a very steep negative slope. So, I'm sorry, excuse me, positive slope. I know this is decreasing, but there's the biggest slope, because this might be the point like 6 or something like that. That means that your slope at -1, because -1 would be here, would be 6, so it would be pretty steep. If I get to like where the 0 is, that might be like 0, 3, so the slope would be 3 there. So the y values on this are the slopes over here. So are you okay with me just putting a plus? What about over here? Aren't those positive again? You're like, I think so. So both of these should have positives and positives. How am I doing? Now, if the slope at 1 is 0, if this point right here on your derivative is 1, 0, then if the slope here is 0, that means we have a flat spot. Now, flat spots don't always end up being turnaround spots, do they? It might end up looking like parabolas, but they don't always. What if you have a graph that does this, gets flat, and does that again? You've seen those before. Some of you have really special names for them, depending on which pre-calc class you had. Yeah, that's what I'm trying to get at. You know what we're doing. We're doing one of these kind of numbers, right? Okay, so all we have to do is make sure that on the first picture we draw, it goes through the origin. Now, the thing I want you to remember is this. The flat spot has to be above or below, whatever the problem is, x equals 1. So if my entire graph is rising here, then let's just pick it to be about right here. It has to be flat around there at 1, whatever that is. And it has to go through this spot right here, because the first part said make sure it goes through your origin. Is this helping a little bit? The second one says do the same thing, make sure above x equals 1, you've got your flat spot. But this time, now we want to make sure that our point goes through 0, 1. So it goes through that. So how do I draw it? The same way we drew the first one, right? Exactly the same way. It'll just have to be up a little bit like this. There's your flat spot. It keeps on going. So they're like, I do want to use this phrase, even though it's really kind of nonsensical. Parallel curves. Do you know what I mean? They're not, I mean, let's face it, guys. Curves can't be parallel because they're going to run into each other, right? But they are kind of parallel curves. One's just 1 unit higher than the other, that's all. So it might look really weird when you look at it, especially on the book, but hopefully, does that help? She's sketching. She's thinking.
Oh, sorry.
Does
Yes.
that help?
Yeah.
Good question. So these were kind of, sometimes I think, especially if I were learning this the first time, these would be harder for me because they're more intuitive. They're not like, here's your algebra formula, now go to town. I'm one of those people that likes, here's the algebra formula, now go to town. I guess it's telling you that I don't like to think about things. That's not really true because I do. But like if I'm learning it for the first time, I'm much more comfortable with here's your algebra, now get started. But the conceptual kind of things, those are a little bit different, sometimes they're a little bit harder to do. Not always, but possibly. Okay, you're silent. Is this a case where the mean lady was saying to you Friday, you can't talk to each other, and you looked at it and went, oh, heck no? So your silence to me is really telling me, I haven't done these, and I don't know if I understand them. You just be as honest as you can, I just need to know where we're at. Yeah.
So, while I was trying to do
Yeah,
it,
yeah, yeah.
I went online,
Okay,
and like,
super.
it made sense,
Okay,
but I'm kind of not, because I didn't know why I was doing it.
Okay.
I just, had to do that.
is my
So like,
explanation helping at all?
for me, yes.
Okay, what would you like to take a glance at now?
Yes. So for 5 and 6,
Mhm.
I knew using the left and then and everything, so I got those.
Okay, given the values of the derivative in the table, estimate what your y value would be at 2, 4, and 6. Okay, keep going. I interrupted you, keep
So
going.
with, I guess with that, like, I understand that too, but then when you look at 7,
Okay.
if you don't get a table, so then
Yeah,
I didn't know how to estimate.
yeah, good point. I mean, I agree with that. Let's see if I can get this fixed. You guys probably picked up a book when you're beginning, but I agree with what Donna's saying. Number 7 gives you a picture. You're like, okay, it's a little bit more like what before. They say in figure 6.10, or 6.10, estimate this. So number 7 says estimate this, which after yesterday, you guys should now be able to tell me what that means in calculus lingo. What's that asking me to do? Find the area, let me say it this way, between your curve and the x-axis. The reason I say that is because this one is below the x-axis, and you learned yesterday part of it is below, part of it is above. So the first part, that was part A. So I'm gonna wing this, it's not gonna be the best graph you've ever drawn, or I've ever drawn, I'll say it that way. It looks to me like it goes through the origin, and it looks like it goes through the point 2, -7. Again, I'm estimating. Looks like it does this, gets kind of flat, sort of starts to smooth out, goes through this 5, 0, and then over here, there's 6 and there's 7 on the right side. Now, it looks to me like it goes 7, and then it kind of peaks in between here and here. My picture looks kind of like that, okay? Now, we're supposed to do, now the reason I say remember this is the area between the x-axis and below, right? And it just said literally estimate, although your paper on here gave you graph paper, okay? They did not, in this section, expect you guys to know anything. Actually, this is the very first section in chapter 6. So they are, like, the people that are doing this problem for the very first time have never, well, yeah, they have seen integrals before. I take it back. They have been able to cut things into rectangles. Okay, so we could cut things into rectangles because actually your graph paper does kind of a decent job. Okay, so we're supposed to estimate, this is the area between the curve and x-axis. So if you guys wanted to, one option would be count your little squares, count partial squares, and just make a really rough estimate. Just remembering this would be negative, this would be positive. So if I take a look at my counting of squares, I have 1, 2, 3, 4, I'm gonna go with maybe I might get something close to 7 down here, -7, if I just sort of estimated and added the partial squares. Like literally, when I looked at this, it looks like it has, wow, that looks way bigger than your picture is. It looks like it has 4 full squares in the middle, kind of goes like this. No, it's not. Well, it might, yeah, then I disagree with what I just, no, it doesn't, because I looked at this and went, that's about -7. Do you guys agree if you look at the window, or if you look at the picture that's drawn there? Okay, so when I see it, I saw 4 full squares, so that area would be -4, okay? And then I just went like, okay, let's kind of just wing the area on the rest of it. And I was like, well, maybe the rest of that is like 3 or 2 more squares. I'm just taking a stab at it without doing any kind of rectangles and adding the rectangular areas. If you guys wanna take a better guess at it, I guess it really does sort of, yeah, I got the dip down part in there. I just kind of thought that this area and this area and this might add up to be like another 3 squares. I'm just kind of estimating. So I kind of went with the area that's between 0 and 5 might be like -7. And then over here, I know this probably is like, that's definitely 1 square. And if you add the other 2, that might be like 1.5 maybe. Or if you guys look at your papers, it's definitely like, I would say the area is probably like 2 on my paper. Because it looks like this, my graph doesn't look quite right. It looks kind of like the part that's here. It would add up to be that to be like +2. So I might say the area 2 is this. So I would probably, if I'm just doing estimation, I'd probably look around -5. Now, if you think your answer is -50, we need to check. You know what I'm saying? Now, you did tell me though, that the y values is counted in terms of 2, right? So I gotta be careful here. This one little box that is 1 unit wide and 2 units tall, I take it back. This looks like this would be 1 area, which means your area is 4, right? Because this is 1, how do I want to say that? This would be 2, and then these 2 guys would be 2. So I disagree with what I just said. So that's probably like this, and then -3. Now, hold on a second, I need to do the same thing down here. I counted like -7 boxes. Let me say it this way. 7 boxes that are -2 in size. So I think this would really be, this is what you were talking about. The y values are in terms of, although 7, no, isn't the x-axis one above? Is the x-axis the line?
Yeah, there's 6 lines.
Oh, I'm getting lost on where the little numbers are. I forgot to, yeah. Yep. It should look like this, right? Yeah, okay, so each one of these boxes, and it goes down to -7. So this is 1, this is 1, this is 1, 1, 1, so I get 6 in there. And then you guys tell me what you think these guys would add up to be. Yeah,
I looked at the solutions for this.
Yeah.
And like counted each box as 2.
yeah, that's what I was gonna say. Because of the way that this is drawn, the way that this, your paper is drawn, it does this. It doesn't have a mark at 7. It went like, this is -2, and then this is -4, and then, does it make sense why they did each of these as, okay, no, whoa. 1, 2, 3, 4, 5, 6, and that did go to 7, so my graph, -8 should be like, is my, okay, we were redrawing here, 101. It would have been better if I just pulled out the computer and did it that way. I probably ought to just do that, because it makes a lot more sense. So we have 1, 2, 3, 4, 5, 6, 7. The graph goes through 5, right guys? It goes through 0, 0. It looks like the minimum spot is at 2. This is -2, this is -4, -6, and then this is -8. So it looked to me like this was going through about here. Somewhere about 2, 7, -7, agreed? And it went like this. It kind of looked like it was the left-hand side of a parabola, and then it got kind of wide over here because it was swung out this way. And then kind of did that. Am I doing better? Now, when we talk about like going across and doing like dotted lines like this, remember, and this is what Danya was talking about, every single time we do this, even though these look like squares, they're not squares, they're boxes that have a height of 2 units every single time we do that. So this has an area of 2, that's 2, that's 2, that's 2. My graph isn't drawn, these were supposed to be 2. If you look at your picture in your book, those are 2 full, there are 6 full squares drawn in that area, in that general vicinity. So just that part would give us 1, 2, 3, 4, 5, 6, -6, right? Then you guys tell me how much extra area you think we should attribute here. If this isn't even a full box, but anyways, I'll just leave it alone. So I get -6 out of the stuff that's in here. How much more do you think the side on the right is? I'm seeing at least 2 boxes, I am, and then maybe another half. So this would be 2, this would be 2, and then that might be 1, because if it's half a box, it would be an area of 1. It would be like a triangle, and then that might be like a full box, that's a one, sorry, not a zero, just put a one over here. It kind of looks like it might be a one just based on what I'm drawing or your pictures. And then, I don't know, over here, do you guys, do you wanna just round this in area would be two, like it would make a full box together, something like that? Okay, so we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, and then do you wanna make it 20? Do you wanna count this as like another area of a box, like maybe half a box? So I'm going with maybe -20. If we do it that way, we look at it when I draw the y-axis in terms of the y is chunked in 2 units apiece. And then we just need to do the same over here, just take a stab in the dark, not stab in the dark, an educated guess on the right side area. The way that I have this drawn looks like this. So this area would be 2 units wide. I'm thinking that this and this would give us maybe an area of 2, and we're supposed to go over to 7, right? 7, yeah, from 0 to 7. What do you think? So this would be like an area of 4 over here. So if we added this with 4, I get about -16. But that's all they really want you to get at. They really don't want you to be any more mathematical or scientific than just estimating, adding boxes 101. We could ask a first grader to kind of estimate the adding of the boxes, but you're like, wow, I know calculus, I don't need to do this anymore. Remember, this is day 1, the gist of the picture, or the gist of the idea. Now, if f is an antiderivative and the same function f and f of 0 is 25, estimate f of 7. Okay. They said if f, this is capital F, but no, f is an antiderivative of the same function, and little f and f of 0 equals 25, estimate f of 7. Okay, so what we just figured out, guys, by the way, when we did this, more of the stuff up here, we just figured out what f of 7 would be. We think it's -16. Okay. Now, if they say to us, part B, if f is the antiderivative, capital F is your antiderivative, so if you guys were to do this, you would have gotten this. Capital F is your antiderivative, that would have meant your area function, okay? Your area function there. Remember what we did yesterday? Plugged in 7 and 0, and we got the area, and so I'm thinking the area is -16. Did you just make a connection? No, okay, you looked like you were gonna say something, that was gonna be like riveting, and I was like, go Rob, say them. Okay, and then they say this, they say, oh yeah, by the way, f of 0 equals 27. And remember, I'm sorry, help me if I copy it down right, f of 0 is 25, and they say estimate f of 7 for this new piece of information. Now, this new original function, this figure drawn right here, is little f of x. This little picture here is little f of x. It's finding the area underneath here. Okay? And so they want to know f of 0 is 25, capital F of 0 is 25, then how's that going to change your area at all? Because this is what this is asking. What's the area between 0 and 7, between the curve and the x-axis? Drawn the original function. You guys aren't looking at your original function. Like, I don't want to say that. When I say original function, you are looking at what you're trying to find the area under. The original function, when we do our actual calculus to it, is always the antiderivative. The antiderivative is that thing. It might be helpful for us. I'm not sure if you guys can tell me to do this. So I draw the first derivative number line just like I did with 1 and 2 and 4. Would you guys agree that 0 is a critical value, and 2 is a critical value, and 5 is a critical value? Would you agree with that? Because each of those replaces where your derivative is 0. Now, let's look at this. Between 0, why did I pick 2? That's not a critical value, that's the one that's where your graph is 0. 0 and 5 are the only places that have critical values. So that's negative, and then this is positive. So your graph is going to be falling, and then it's going to be rising. Now, I want you to think about trying to sketch my original function. I didn't give myself enough space here to sketch my original function. So if I try to sketch this, I don't know that I gave myself enough space, probably not. Let me make this x-axis move up 2 times it. Our graph needs to be falling, and then should also be flat at 0. So I don't know what it is at 0, I don't know if it's something like that, or I don't know if it's like a chair kind of thing, it could be one of these kind of things. But I do know that below 5, the graph is supposed to be something like this. Oops, that graph not good, let's make your point way down. The graph is supposed to do something like that. Agreed? Okay, now, what it's saying is, if I draw this, I've assumed right now that my curve goes through 0, 0. But it's saying that your curve, instead of going through that, it's saying that your curve f of, what is it again, 0 is 25. So what's that do to your graph that I just drew here? It takes the graph and moves it up 25 units, right? So understand that, it takes my graph and moves it up 25 units. So if I found f of 7 is negative 16, and this is going to move the graph up 25 units, should I now be able to say f of 7 on my new graph is moved up 25 units, or this is included, should be 25 plus negative 16? You see what I'm saying? Okay, so I would come up with, I think that's 9. Does that help out? It's just a really hard question, because you're not visually seeing it. And I could redraw this 25 units higher, I'd be drawing into my work above it, not to be confused with the shape that's here. It's not finding the area under this, it's just trying to find the y value of the curve on that one. That's a tough question, flat out, it's just a tough question. And remember, I believe that I've stuck, I hope I put them on your Blackboard page, but I'm not sure if I have yet. I scanned in all the answers for these chapters. They should still be in your Blackboard site, are they, guys? The full solution manual?
Yeah.
Okay, I hope so, because I had to go past chapter 8, because the other class is in like, I don't know, 10 or whatever it is. I think I've scanned up through chapter 11, I don't know if it's stuck them on your site, so we won't get to like chapter 11 in your class. We don't have to go that far. Not because we're behind, we just don't need to do it. Trust me, that's joy and happiness. Yeah, that's all I'm gonna say. Okay. Joy, happiness, bliss. What else would you like to discuss? Other questions on this page? You have 2, 8, 10, 11. So these are like, what are the critical points? Which are the max and mins? I would tell you guys that I think 9, 10, okay, 9 isn't one of the ones you have to do, 10 is, 11 is, those are big time important, 12 I didn't give you, 13 I didn't give you, 14 would be kind of probably a good thing to understand, be able to do, 15, same kind of thing, similar, 18, yes ma'am, I do see your hand, I'm not ignoring you, I promise, which one? 11, awesome, okay. Now, I should probably just be using the picture that's in the book, but I'll go ahead and draw it myself. But here's one. Okay. Now, what we want to first do is ask this question. I'm going to ask you rather than read the instructions, because I want you guys to get in a better habit than I do. What am I drawing when I draw this picture? Am I drawing the function that I'm finding the area under? Am I drawing the original function? Read me the instructions. What am I sketching? It says little f of x. You're like, I'm asking you what that means. You're like, I don't know. If I knew, I wouldn't ask you, lady. I'm telling you to answer questions. So, it says at the beginning, let f prime of x equal little f of x. Let me explain why that is what it is and what it means to you guys. When and if we did a problem like this, remember yesterday I taught you about how to do these kinds of problems with calculus, where you add 1 to your exponent, you do 1 over that in the front. A lot of times in calculus what we'll do is we'll write it this way. So this is the function I'm finding the area under, always. Okay, you're always finding the area under little f. But when we do the calculus, do this. So let me put an equal sign here. You can put CALC for not calculate the calculus. What we sometimes do is call the original function capital F of x. So just understand, remember the relationship between this was the function you're finding the area under, but this one ends up being the derivative of the original function. Do you guys follow what I'm saying? There's 2 relationships here. One of them just has to do with area. This is always what you're finding the area under, and then this will give us to, this will get us to what the function value is, or what the original function was. This is the derivative of that. And so what they told us in this right here is that f of x, little f of x, is the derivative of capital F of x. That means that if I do this and do the antiderivative of it, I'm going to get this. Or if I do the derivative of this, I'm going to get little f of x. And that's literally what this says. Do the derivative of capital F and I get little f. So this is saying that that's my relationship. It's just not giving me a specific function. Algebraically, it would be like if I said to you guys, x squared dx is your original function, and then we did the rule from yesterday and you would have come up with that. Do you follow what I'm saying here? So this would have meant I was finding the area underneath y equals x squared, and this is my formula. So if I were trying to do the area between 0 and 2, I might be doing like this area here. I would come over here, plug in 0 and 2, and I'd find my answer. Okay? Now, when I find my answer, what I end up with here is plugging in 2, that means plugging in your function, your actual function, plugging in 2, and then plugging in 0. That's what that's really doing. So understand that. Now, let's go back with number 11 and what are the other directions. The other directions in 11 are, what are the critical points of f of x? So your original function, what are the critical points? Are they local max? Which critical points are local maxima? Which are local minima? Which are neither? And sketch a possible graph. Very similar to what we've already done. I wish I hadn't drawn that right there, but I did. That's okay. Because what I want to do is go, that's the derivative graph. Different ways we can go through this, but that's your derivative graph. So we'll do this once again. And I kind of like this problem because I don't know what x1 and x2 and x3 are. Is x2 corresponding with the middle of the dip? Is there an x2 on your graph, guys? No one's talking to me. Okay, I go to the middle. Alright, so x2 looks kind of like that. Alright, so if we did this, oh, I did it up there again. That was kind of stupid. Okay, I'm not trying to draw the original function up here. The original function, I don't know what it looks like. My number line is here, and then the derivative was down here. So here's the derivative. Looks like this. There's x3, x1, and then x2 goes with that. So my number line should say this. Do you guys agree with me this is an x-intercept? So that means that right above it at x1, that's a critical point. And then right above this at x3, that's a critical point because it's an x-intercept, right? And this graph on 11 just stopped right there. It didn't go any further past that. Did it look like it went above the x-axis? Mine does, but your print might be a little bit. I find that the blue graphs are printed off in some of the textbooks. It's a little hard to see. Okay, so tell me this area right in here, what kind of y values do you have over here, positive or negative? Positive. So these are positive between 0 and x1. I can't say anything to the left of 0 because they didn't give me any information about it. They didn't tell me anything to the left of 0. Between x1 and x3, do you notice, sorry, my sleeve, probably your finger erased that. Do you see between these two, they're all negative? The slopes are all negative? You guys know that means, oh, excuse me, I'm thinking of concavity. You know that that means your graph is rising and that means your graph is falling, right? And then over to the right, it looked a little bit to me like it was up positive, but I don't know in your book if it does. I would just say we're going to stop here and call it a day. I don't think we were given much of a graph beyond that. Okay, so let's do this. Let's draw it. What do you think happens? You can already tell me what happens at x1. Is it a max or a min? It's a max. Can't you see that stick figure mountain picture sitting in front of you? So the question was, is it a local max or local min? We have to say local because we don't know what the rest of the curve does. But we clearly know that our graph above x1, and I don't know where the height is. It could be any of these points. It might even be down here. But I know my graph is rising until it gets to that point and then falling. I know for sure that it's doing that. And I don't know if it's an x-intercept, but do you see what I mean by like parallel curves? You have a ton of them, a ton of different possibilities. Okay, so I know that it's a max, and then sketch a possible graph. I just sketched about 4. So it's doing the same thing, just asking it in a weird way, asking a different kind of question. Do you agree with this rises until it gets to here and falls after there? We end up getting a max at that spot. Now, I'll just leave that alone. That's all I was going to say. Actually, it should probably be a little bit more, let's say slope is 0 here, this should have a flat spot also at 3, guys. But here's the thing, I don't know if it's about to have like a turnaround spot like this, or if it's gonna do one of these. So this graph should be flat above x3, and then I'm not really sure. Just know that it gets flat. That's all I can kind of say, and it just stops because we don't know what the graph does on the right side. Do you follow what I'm saying there? Because the slope here is 0, so I know it's flat, but I don't know if it's about to dip around and be like the bottom of Florida, or if it's a Tina, or whatever you guys call them, a C, or whatever those are. Okay, so the plan for tomorrow is for you to go back to yesterday, when I was here and helped you with how to do the area underneath the curve. And I will give these to you now, so that you don't not have them, don't lose them. These, you don't have to do them tonight. You're going to be doing them in class tomorrow. You may work with each other. They're all checkable on your calculator, but the idea is not to do them on your calculator.